types of intermolecular forces. We've been talking a lot about the effects of these intermolecular forces. Now we're going to actually talk about what they are. Intermolecular, we mentioned this earlier. It doesn't hurt to repeat this. Intermolecular, between molecules. We're not talking about covalent or ionic bonds. These are between molecules. The strength of these forces determines whether that substance is a liquid, solid, or a gas at a specific temperature. When you have strong intermolecular forces, you're going to have liquids or solids. And when you have weak intermolecular forces, you're going to have gases at room temperature. So these are the different types. The first one we'll talk about is called a dispersion force, which is a name that's commonly used. It's not my favorite. My favorite name for this force is induced dipole force. These are also called London forces or London dispersion forces, and they're also sometimes called van der Waals forces. We've got all these crazy names. This is the intermolecular force that all molecules and atoms have, all of them. And these are caused by fluctuations in the electron distribution within the particles of the matter. All atoms and molecules have electrons. All substances have dispersion forces. What happens is that the electrons in an atom or a molecule at any given instant might be unevenly distributed, might be kind of lopsided. When my husband and I got married, we spent a couple days of our honeymoon in San Francisco. And we went on one of those blue and white cruises around the San Francisco Bay. It was kind of fun. Big boat, but lots of people on it. So I think of a boat like that as being a molecule or an atom, and the people being like the electrons. And most of the time, the people are going to be sort of randomly, evenly distributed around the boat. They're not all going to be on one side. Except when you go past something really interesting, like maybe you go around Alcatraz and the tour guide is saying, look, 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 and all the people from the other side of the boat come to the one side of the boat to look at Alcatraz. Now, does that cause the boat to capsize? No, but might it list just a tiny bit if all the passengers are on one side? It might tip just a little bit, not be quite straight up and down. That's what can happen with the electrons in an atom or a molecule. They can just kind of randomly be distributed in a lopsided way. Also reminds me of my children. I have six kids, and usually they're just kind of spread out all over the place. But occasionally something, there was one day I came into the living room, all 6 of them were on half of the couch. Why? I have no idea. I took a picture because you don't often see them all so close together. It can happen, and the electrons can kind of bunch up too. It's not their normal state, but it can happen. And so we get this uneven distribution. So here is an example of, or an illustration of a helium atom. And here are the 2 electrons in helium. And here they're, pretty much spread out. And in frame 2, they're still pretty much spread out. And here, maybe helium's going past Alcatraz, and both of the electrons go to this side of the atom to look at something. This causes a distortion in the charge distribution. Now we have the 2 negative electrons on this side, and nothing negative over here, just this positive nucleus. So this side of the atom becomes partially positive. So lowercase Greek delta, meaning a partial charge. This side's partially positive, this side is partially negative. It's not normally like that, but it can spontaneously happen. It's called an instantaneous dipole or a temporary dipole. It doesn't last very long. It's fractions of a second, and it's gone. But when that happens, it can affect a neighboring molecule. So here's this one that got lopsided on its own. This side's negative, this side's a little positive. This positive side attracts the electrons in a neighboring atom. They're like, oh, there's something interesting. And so they become lopsided. And now we have a negative and a positive charge, and we've got a weak attraction between these two atoms. This one's lopsided, and it induces a dipole in the next one. That's why I like the name induced dipoles. You get one random dipole, uneven distribution of charge, and it induces a dipole in a neighboring atom, and then there's attraction between them. And then this dipole goes away, and then these guys lose interest, and it all goes away. But it comes and goes and comes and goes and comes and goes many, many times a second. And so even though the amount of attraction is very brief and very small, because there's so many of them, it can become significant. So the dispersion force happens as neighboring atoms attract one another. These dipoles are transient, constantly appearing and disappearing. The magnitude of the force depends on how easily the electrons in that atom or molecule can polarize, how easily they can get lopsided in response to a neighboring molecule. And that's going to depend on the size of the electron cloud. A larger electron cloud is more easily polarized. So I kind of think, sometimes I think about family size. And so say you have a mom with 2 kids and they're going to the fair. We don't go to the fair anymore because it just seems like a great place to lose money and children, right? But this mom's going to the fair and she's got one child with her left hand and one with her right hand. She's holding their hands and they're walking through the fair. These children are not going to be able to both be on the same side of mom as easily as if I went to the fair and I'm holding on to the 2 youngest, but the other 4 are free to do whatever they want. And they could just run off over here and our family unit could get lopsided, all the kids on one side of mom. Larger molecules, the atoms are farther from the nucleus, and so they're more easily shifted around. And so what we see is that as the atom gets larger, the strength of the intermolecular force becomes larger. Now, we can't base that on molar mass alone, but it can be helpful as a guide when we're looking at similar elements or compounds. So if we look here at the noble gases, helium, neon, argon, krypton, xenon, there is a trend in their molar mass. As we go down the group in the periodic table, we've learned the size of the atom gets larger. The molar mass also gets larger. And look what happens to the boiling points. Helium boils at 4.2 Kelvin. That's 4 degrees above absolute zero. It's hard to get liquid helium. But neon boils at 27, and argon at 87, and krypton at 120, and xenon at 165. This higher boiling point indicates that the strength of the attractions between the atoms is larger. Xenon has a larger molar mass. The atoms are larger. They're more easily polarized. And so these dispersion forces are stronger. Helium is very small, very, very weak dispersion forces. And so he boils at almost nothing. Does that make sense? Boiling point is related to strength of intermolecular forces, the stick-togetherness of them. And this first form of stick-togetherness that we're talking about, the dispersion forces, depends on the size of the molecule or the atom. So we should be able to predict things like this. Which hydrocarbon, CH4 or C2H8, H6, my eyes are going, has the higher boiling point? These 2 compounds are similar. They're both just carbons and hydrogens. What's the difference between them? One's larger, right? C2H6 is larger than CH4. Larger size, what does that do to the strength of those dispersion forces? larger dispersion forces, stronger dispersion forces. Stronger forces affect the boiling point because now the Velcro on these molecules is stickier. There's more Velcro. And so in order for them to break loose, they have to move faster, which means they have to be at a higher temperature. So which one's going to have a higher boiling point? The C2H6. Does that make sense? The second force is called a dipole-dipole force. And this is an interaction between one dipole and another dipole. And this one exists in all polar molecules. Dispersion forces exist in all molecules and atoms. Dipole-dipole forces exist in polar molecules. If you have individual atoms, you can't have dipole-dipole forces because atoms cannot have a permanent dipole, only polar molecules. Polar molecules have permanent dipoles. They're always lopsided. So the dipole-dipole force, interaction between the positive end of one dipole and the negative end of another dipole on a different molecule. We observe that polar molecules have higher melting and boiling points compared to nonpolar molecules of similar molar mass. When the molar masses are similar, then we know that the dispersion forces are similar. So this is a model of formaldehyde. Here's its Lewis structure, and here's the molecular model. This end is going to be partially positive because hydrogen has a low electronegativity, and this end is going to be partially negative because oxygen is more electronegative. So we've got a negative end and a positive end. If these two molecules are near to each other, the positive end of this one attracts the negative end of the other one. And this is a force that's always there, unlike the dispersion forces that come and go and come and go. And so this one's always present, it's going to be stronger. If we compare formaldehyde with ethane, C2H6 and formaldehyde we just looked at, here are their Lewis structures. Does this molecule look polar? Does it look lopsided or does it look nice and symmetrical? It's nice and symmetrical. And my little, two little rules, if there's no lone pairs and all the atoms bonded to the central atom are the same. Well, this one has two central atoms, but there's no lone pairs anywhere, and all the atoms around are hydrogens, they're all the same. Here the central atom is carbon, there's no lone pairs on it, but the oxygen is different, and so this one's lopsided, this one's polar. Their molar masses are almost identical. Look at their boiling points and melting points. Formaldehyde boils at -19, ethane boils at -88. This boils at a much lower temperature because this only has dispersion forces. This has dispersion forces and dipole-dipole forces, which are stronger. Any questions? Polarity of molecules is really important. It affects these dipole-dipole forces, which affect temperature of melting and boiling. It also affects miscibility. Miscibility is the ability of a liquid to mix with another liquid. We don't say solubility, we say miscibility. And to help you remember, it's a little bit like mixability, right? That's not actually a word, but mixability. Will the liquids mix? If they mix, they're miscible. In general, polar liquids are miscible with other polar liquids, but they are immiscible, which means not miscible, with nonpolar liquids. So we have this idea of, we talked about solubility, like dissolves like. Well, that applies to liquids and miscibility as well. In a way, you could think of these types of intermolecular forces as being a language, right? So I am of Swedish descent, my husband is of Japanese descent. So I can pick on those two nationalities without being politically incorrect, right? So say you had a room full of people, and there's two groups. There's a bunch of Japanese people who only speak Japanese, and a bunch of Swedish people who only speak Swedish. It's not really a great illustration because in both of those countries, most people also speak English, but we're going to pretend they don't. Are the Swedes and the Japanese going to interact with each other? No. You're probably going to see a group of Swedish people over here and a group of Japanese people talking in Japanese and a bunch of Swedes over here speaking in Swedish. There might be several clusters of conversation, but they're not going to mix well, are they? They can't communicate with each other. So the dipole-dipole forces are like one language of interaction between molecules, and then dispersion forces are a different language. The dipole-dipole forces of attraction are very, very strong. And so when we have something like water, which is polar, it has very strong forces of attraction, and it excludes the nonpolar molecules. Oily hands, oily stains on your clothes, you can't just rinse them away with water because the oil does not mix with the water. Here's an illustration showing the molecular structure here. The water molecules are polar, the oil molecules are nonpolar. They'll form two distinct layers. I actually have this very same cruet at home, and here you've got some Italian salad dressing, right? And here's the oil on the top and the vinegar with some spices and stuff in the bottom. This is mostly water. Vinegar's mostly water. You can shake it up, but as soon as you put it down, it begins to settle out. The water molecules are so strongly attracted to each other that they squeeze the oil out, and the oil goes to the top because it's less dense. And here's a picture of an oil spill. You get a tanker that's leaking oil, and the oil sits on top of the water. It doesn't mix around and distribute throughout the whole ocean. It just sits on top. That causes a big problem for wildlife because the birds come and land in that, and then they get all oily. So all polar molecules have dipole-dipole forces. Polar. All particles, molecules, and atoms have dispersion forces. That's the name your book uses, dispersion forces. All polar molecules have dipole-dipole forces. How do you determine if a molecule is polar? Well, here's the book's method. See if you have polar bonds and then identify whether they're going to add together to form a net dipole moment. Or you can use my method, which works most of the time. A molecule is nonpolar if both of these conditions are true. This doesn't always work, but it usually does. No lone pairs in the central atom. The atoms bonded to the central atom are identical, or they have the same electronegativity. So you should be able, with a relatively simple molecule, to identify whether it's polar or not. So determine whether each of these molecules has dipole-dipole forces. This is CI4. It's not Cl4, that's why I put the name, carbon tetraiodide. It really helps to draw Lewis structures for these. So that's carbon with 4 iodines. We only care about the lone pairs on the central atom. The iodine atoms are around the carbon. There are 4 of them. There are 4 single bonds here. Is carbon going to have any lone pairs in its Lewis structure? No, because the 4 bonds give it 8 valence electrons, right? So there's no lone pairs on the central atom, and all of these atoms that are bonded to it are the same. That means that this molecule is symmetrical. It is not polar. If it's not polar, does it have dipole-dipole forces? No. Only polar molecules have dipole-dipole forces. So that one's a no. How about CH3Cl? Again, there are some lone pairs on chlorine, but we don't care about them for this. So here's carbon. It's bonded to 3 hydrogens in a chlorine. That gives it its octet of electrons. So no lone pairs. Are all these atoms the same? No, chlorine's different. And chlorine has a different electronegativity than hydrogen. So that makes this molecule polar. Does it have dipole-dipole forces? Yes. All polar molecules have dipole-dipole forces. How about HCl? Well, we don't use my rules for this because there's no central atom. But is this a polar bond? Are the atoms different? They are. Usually if the atoms are different, it'll be polar. That doesn't always work, but it works enough of the time that you can just go with that. So these are different in electronegativity, so it's going to be polar, and this will have dipole-dipole forces. Any questions? The last type of intermolecular force is called hydrogen bonding, which is kind of a confusing name because that makes it sound like it's a covalent bond of some sort, and it's not. It's an intermolecular attraction. If we have polar molecules that have hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen, that's an especially polar bond, and so the dipole-dipole force that's experienced between two such molecules is extra large. In fact, it's so large that it's given a special name. It's called a hydrogen bond. It's sort of a super dipole-dipole force. And so we need to be able to recognize which molecules can have hydrogen bonding. Did you see the movie E.T.? What did E.T. say? He would point and say, "Phone home." F-O-N with H. Like that? So this is like that, home. Phone home. So if you have a polar molecule and you have fluorine, oxygen, or nitrogen that is bonded to hydrogen, it has to be bonded directly to a hydrogen, otherwise it doesn't count. Then you have hydrogen bonding. Polar molecule, ET, phone home. The reason that these have such a strong attraction is that fluorine, oxygen, and nitrogen are the most electronegative elements, and hydrogen is one of the lowest in electronegativity. And then we also have these guys being small, and so the molecules can get very close together. When you have these electrostatic attractions between opposite electrical charges, how close they can get matters a lot. Electrostatic attractions are a lot like magnetic attractions. And you can try this at home. You put a magnet on your refrigerator. It sticks, right? Put one piece of paper and stick the magnet on there. And then do 2 pieces of paper, and 3 pieces of paper, and 4 pieces of paper. And depending on how strong your magnet is, at some point you're going to come up with a number of pieces of paper that the magnet will not stick anymore. Why? Because the distance between the metal surface of your refrigerator and the magnet has gotten too large. These forces of attraction are very sensitive to the distance of separation. And so because these atoms, fluorine, oxygen, nitrogen, and hydrogen, are all very small, they can get really close together, and so we have these significant forces called hydrogen bonding. So here we have an illustration of this with hydrogen fluoride. Here's hydrogen and here's fluorine. The electronegativity difference is large, and so this partial positive charge is larger than it would be on like a hydrogen sulfur or hydrogen chlorine bond. So the deltas here are a little bit bigger, and here we have this negative attracted to the positive and this negative attracted to this positive. And these red dotted lines, those are the hydrogen bonds. They are not actual bonds. We call them hydrogen bonds. I know that's confusing, and I'm sorry. I'll apologize for my profession on that one. Let's look at what happens with methanol. Methanol has oxygen bonded directly to hydrogen. These hydrogens bonded to carbon don't matter for hydrogen bonding. The electronegativity difference is not large enough there. But oxygen to hydrogen, that's the key. So this hydrogen is partially positive, this oxygen is partially negative. And this hydrogen is attracted to the oxygen in a neighboring molecule. And we get hydrogen bonding. We can compare the effects of this. Here's methanol and ethane. Earlier we compared formaldehyde with ethane. Again, we have similar molar masses. This one's a little bigger, but still 32 and 30, very close. This one we learned was nonpolar. What kind of intermolecular forces does a nonpolar molecule have? The first one started with a D. Well, the second one started with a D too. Dispersion forces. So this one only has dispersion forces. This molecule, we see on this carbon here, we've got 3 hydrogens and an oxygen hydrogen, and both the carbon and the oxygen here are lopsided, and so we can identify this as a polar molecule. And here we have an oxygen-hydrogen bond. OH, phone home, FO, or N with H. We've got the O. So this is going to have hydrogen bonding. Look what happens to the boiling point. Boiling point of ethane, minus 88. Boiling point of methanol, plus 64.7. Much, much higher. You have to put a lot more energy into it. You have to raise the temperature much higher before these guys can break free. We talked about playing Red Rover. Okay, these guys, the Red Rover line is much stronger. Hydrogen bonds are the strongest of the Red Rover lines, and dispersion forces are the weakest. You can get through these guys so easy. You barely have to touch them and they'll let go and let you through. These guys, you're going to need to get a running start. You're going to have a much higher temperature. Any questions? Here's what it looks like in water. Water molecule, our little Mickey Mouse guys here. The hydrogen end of the molecule is positive, the oxygen is negative. And so we get this attraction between the hydrogen of one and the oxygen of the other. And so we get multiple hydrogen bonds between the molecules. Boiling point of water is 100 degrees, which is really high for a molecule with a low molar mass of 18. Look at these guys. This was 32. That's almost twice the molar mass of water. Its boiling point is 64. We would expect the boiling point of water to be lower than this, but it's not. It's actually significantly higher due to the hydrogen bonding and due to the multiple possibilities for hydrogen bonding. Hydrogen bonding is a very, very important force. I think you've probably all heard of DNA, right? You have DNA in your body. So DNA has a double helix. It has 2 individual strands that are held together and coil up like this. And what holds the 2 strands together is hydrogen bonding. These are the base pairs that are present on these strands of DNA. Can't read. Thymine and adenine. And here we have an oxygen, and here we have a nitrogen. And the nitrogen, here we have nitrogen bonded to oxygen, hydrogen. Nitrogen, hydrogen bond, and this hydrogen is attracted to the oxygen here. This nitrogen has a hydrogen and is attracted to that nitrogen over there. And so we have 2 hydrogen bonds occurring between thymine and adenine. Between cytosine and guanine, cysteine. No, it is cytosine. It's too small, I can't see it. I should read it on the screen. Cytosine and guanine. There's 3 hydrogen bonds that form. And so this enables DNA to replicate, because if you have thymine, guanine and cytosine will not hydrogen bond effectively with thymine because they don't have the right spacing. They don't line up just right, but adenine does. And so we always have these base pairs, they're called. And you can take one strand of DNA and you can reproduce it by making the complementary strand. And that's what happens in your body when your cells replicate. It's a very cool process. and wouldn't be possible without hydrogen bonds. This is a chart comparing the types of intermolecular forces, what sort of molecules they're found in, and their relative strengths. And so that can be a good reference. So which has the higher boiling point, HF or HCl, and why? Any of these questions where they're asking you to compare boiling points or melting points or anything like that is going to come down to intermolecular forces. So HF and HCl. The first thing to do is to determine, are these molecules polar or nonpolar? They're polar. They're both polar, right? They're both polar. All molecules have dispersion forces. They're both polar. They have dipole-dipole forces. So at that point, they're essentially the same. Is one of these capable of hydrogen bonding? Yeah, HF can hydrogen bond because we have an HF bond. Here we've got hydrogen, but it's not bonded to nitrogen, oxygen, or fluorine. So this one is polar and has hydrogen bonding. So which one has the higher boiling point? The HF. Stronger forces of attraction, higher boiling point. Any questions?